In this video, we're talking about how to solve radical equations, and there are two really important things to remember when you're solving radical equations. The first is you're always trying to isolate the radical in your equation onto its own side of the equation. The reason you want to isolate it is so that you can square both sides of the equation, because when you square a square root, those two things cancel with one another and you'll just be left with what's inside the square root. That's how we're going to eliminate the square root sign from the equation in order to solve for our variable. The second thing you need to remember is that you always have to double check the solutions that you find to the equation. When you're dealing with radical equations, this is not an optional thing. You have to do it. And the reason is because whatever potential solutions you find to the radical equation may not actually satisfy the original equation. So you always have to double check to make sure that your solution or solutions are truly valid. So in this first example, we have the square root of x minus 2. And then outside the square root, we have minus 6 is equal to 0. So we know this is an equation because we have an equal sign. We know it's a radical equation because we have a radical or a square root involved. So our process is going to be to try to isolate the square root by itself. In order to do that, we'll have to add 6 to both sides of our equation so that we can cancel the negative 6 and the positive 6 on the left. When we do that, that'll leave us with just x minus 2, or square root of x minus 2, is equal to 0 plus 6, or 6 on the right, because we get these two to cancel. So now we've isolated our square root, and once we have our square root isolated, we want to go ahead and square both sides of the equation. Remember, whatever you do to one side of the equation, you have to do to the other in order to keep the equation balanced. And as we said before, when we square a square root, those two things cancel, leaving us with just whatever's inside the square root, in this case, x minus 2. On the right-hand side, we get 6 squared, or 6 times 6, that's 36. And now to solve for x, we just go ahead and add 2 to both sides of the equation. We get negative 2 and positive 2 to cancel on the left, leaving us with just x is equal to 38. So now this is our potential solution to the equation, but in order to verify that it's an actual solution, we must plug this back into the original equation to make sure that the equation is true. So plugging x equals 38 back into our original equation, we get the square root of 38 minus 2 minus 6 equals 0. We get the square root of 36 minus 6 equals 0. The square root of 36 is 6, so we get 6 minus 6 equals 0, or 0 equals 0. So this checks out, that's true, which means that x equals 38 is in fact a valid solution to our radical equation. Let's look at a second example here. We have the square root of x plus 6 plus x equals 0. Just as before, our goal is going to be to isolate the square root on its own side of the equation. In order to do that, we'll have to subtract x from both sides of the equation. That'll get positive x and negative x to cancel, leaving us with the square root of x plus 6 is equal to negative x. Now that we have the square root isolated on its own, we can go ahead and square both sides of the equation like this. When we square a square root, we get those two things to cancel, leaving us with just what's inside of our square root. So we get x plus 6 is equal to, and now we have negative x times negative x. So be careful with your negative signs here. Remember that this is two factors of negative x, or just negative x times negative x like this. When we multiply two negatives together, they cancel to become a positive. So we just have x times x, or x squared. So we get x squared here. And now what we need to do is get all of our non-zero terms on one side and get this equation equal to 0. So the way that we'll do that, we want to keep our x squared term positive whenever we can. We're going to subtract x and subtract 6 from both sides, so minus x and minus 6, so that we get positive x and negative x to cancel, and positive 6 and negative 6 to cancel. That's going to leave us with just 0 on the left, and on the right, we'll get x squared minus x minus 6. Now we have just a standard trinomial that we can factor, so we're going to say 0 is equal to x minus 3 times x plus 2. And if we want to double check to make sure that we factored this correctly, we can say x times x gives us x squared plus 2x, and a minus 3x gives us a minus 1x, or minus x, so that's right. And then a negative 3 times a positive 2 is a negative 6, so we get back to negative 6. So we factored correctly this trinomial above, and now we can use the zero theorem to solve for x. Remember that the zero theorem tells us that if p times q is equal to 0, then either p is equal to 0 and or q is equal to 0. And the reason that we know that that's true, of course, is because if p times q is equal to 0, then in order to make this equation true, either p must be equal to 0, so that you get 0q equals 0, or just 0 equals 0, or q equals 0, where you'd get 0p equals 0, or just 0 equals 0. So the only way this equation is true is if p equals 0 or q equals 0. Well, if we compare this zero theorem formula to our equation, what we're saying is that p is basically this factor here of x minus 3, and that q is this factor here of x plus 2. So our equation is really p times q equals 0, just like our zero theorem formula. So what that tells us is that the solutions then are each of these factors set equal to 0 individually. So we can set x minus 3 equal to 0, and we can set x plus 2 equal to 0. Solving both of these will get x is equal to positive 3 when we add 3 to both sides, and subtracting 2 from both sides over here, we get x is equal to negative 2. These are now the potential solutions to the original equation, but remember, we always have to plug them back into the original equation to make sure that they're actual solutions. So let's start with x equals 3 and plug that back into our original equation. We're going to get the square root of 3 plus 6 plus 3 is equal to 0. 3 plus 6 is equal to 9, so we get the square root of 9 plus 3 equals 0. The square root of 9 is 3, so 3 plus 3 equals 0. 6 equals 0, and that is not true. 6 does not equal 0, which means that x equals 3 is not an actual solution to the radical equation. Let's try x equals negative 2 here. We're going to get the square root of negative 2 plus 6, and then we get plus negative 2, or just minus 2, equals 0. Negative 2 plus 6 is the same as 6 minus 2, so that's 4. So the square root of 4 minus 2 equals 0. The square root of 4 is 2, so we get 2 minus 2 equals 0, or 0 equals 0. That does check out, which means that x equals negative 2 is in fact a real solution to our radical equation. So that's a perfect illustration of why you always, always, always must check your answers back into the original equation, because the solutions you find here are not always going to satisfy the original equation. And in this case, x equals 3 looked like it was a potential solution, but didn't turn out to be an actual solution, and x equals negative 2 was the only solution to this radical equation.